Hello everybody, this is the data storage video in the large-scale machine learning section of ML Expert. In this video, we're going to be going over exactly what this storage layer actually is. In the previous videos, we talked about the producers and the brokers and even a little bit about the consumers, but we didn't reference them any more than just calling them storage. So let's actually figure out what that looks like. So let's say that we have a single machine, a single computer here, and this computer has 4 HDDs, or hard disk drives. Each of these drives can read and write at about 100 megabytes per second in terms of rate. That's how fast we can read and store data from each individual drive. Well, let's say that we have 1 terabyte of data. We distribute this terabyte of data across all 4 by putting 25% of the terabyte on each individual drive. If we did this and parallelized the process, it would take about 40 minutes for 1 terabyte to get written or read from the entire computer. Additionally, since we are just dealing with one host, there would be no replication. So if anything were to happen to this host, your data is gone, or if anything were to happen to each of these individual drives, roughly that portion of your data would be gone. So let's say instead that we had 10 machines here, we still had that 100 megabytes per second read and write capability for each hard disk drive, and this time we want to read or write 1 terabyte of data. If we had this configuration here, it would take roughly 15 minutes. This is because we're storing 1/10 of a terabyte per drive instead of 1/4 of a terabyte per drive. So what we actually bought was a speed up here in read and write time. In order to get this speed up, we had to distribute the data across more than just a single host. So another thing that we can do, since we're dealing with more than a single host now, is replicate this data across that same cluster of hosts as we had the original data stored in. So here, these would be the replicated data, and the orange there would be the original data. So at the cost of adding a larger number of hosts, we've bought a faster read and write time, as well as the ability to more effectively replicate our data. Now, I suspect we don't want to implement a system like this on our own, so we can actually use a tool called Hadoop Distributed File System. In essence, this is exactly what we've just reviewed. Basically, there are data nodes associated with this distributed file system. These data nodes exist on machines that actually store your data for you. You have a name node in HDFS, which keeps track of which data is on which data node. Here, a user would use the HDFS client. They would present a file to the client. The client would partition that file up into smaller blocks. Here the blocks are A, B, and C. It would then send A, the first part of the partition file, to the name node, make a request, effectively saying, hey, I want to store this block here. The name node would say, okay, contact data node 1, 2, and 3 to store block A. The HDFS client would then store A across 1, 2, and 3 of the data nodes. We're storing 3 copies in order to replicate the data. Then we send B to the name node, which is the block or the partition of our file. The name node will figure out which data nodes can have B stored on them, and it will say store B in the data nodes 1, 3, and 4. The same process would continue for partition C of the file. So now we have our file distributed across the Hadoop distributed file system. The partitions, or the blocks of the files, are stored across data nodes, and the name node keeps track of the original file as well as its partitions and the locations of each of those partitions. This is useful such that the user could then use the HDFS client to get the particular file that they just stored. They would use the name node to retrieve a map such that the key would be the part or the partition of the file, and the value would be all of the data nodes in which the block is stored on. So here, when we're looking to get partition A of the original file that we wanted to store, it would look first at node 1, Now, if data node 1 is up and running just fine, it would then collect block A from that data node and continue on to collect the next blocks. However, if this data node is actually down or not working or not available, then it would go to the following node that block A is stored on. Here, that's data node 2. So it would visit data node 2, and hopefully that node is up, available, and has A. The same process would continue for all of the subsequent nodes. The HDFS client would then put back together the original file from these partitions and return the file to the user. The good thing about HDFS is that it is very scalable. Given enough data nodes across a particular cluster, we can store tens of petabytes of data. One of the problems, though, of HDFS is that the name node is a single point of failure. If the name node goes down, then the HDFS client can't contact it to read or write files. So what we can do, in the case that the name node does go down, is actually have two name nodes running side by side. One name node would run in the active state, the other name node would run in the passive state, and anytime the active node goes down, the passive name node would then become active and take its place. Meanwhile, we could replace the past active name node. This is a way to achieve high availability, and this particular configuration is called a hot standby. By hot standby, we mean that this passive node is consistently in sync with whatever information is on the active node. How they stay in sync is they use something called a journal node cluster. So here, the journal node cluster will actually be written to by the active node and read from by the passive node, such that if the active node goes down, the passive node just has to make sure it's up to date with the journal node by performing a few more reads, and then it will be up to date enough to be the new active name node. So as well as the name node failing, it's very possible, and it should be expected, that one of the data nodes will fail. In order to discover when a data node is inactive, what we can do is use the name node to perform heartbeat calls to all of the known data nodes. A heartbeat is just a call out to the particular data nodes such that they must respond, "Yes, I'm healthy." If a particular data node doesn't respond to the heartbeat after some number of tries, then the name node will just replicate that data node's data to other nodes in the cluster. Now, in the case that the name node that's currently active gets isolated due to some network failure, it will still believe that it's active and could come online soon, but instead we want to promote this passive name node to be the active, so we have to make sure that only one name node is active at a time. For that, we use something called a zookeeper cluster. Zookeeper will manage different heartbeat connections between each of the active and the passive nodes, and with some additional tools will ensure that only one name node is active at a time. Now, as an additional technicality, Hadoop 3 doesn't actually replicate the data in its entirety. It uses something called erasure coding. So imagine here if we had this expression. So this here is XOR. So we had 1 XOR 0, XOR 1, XOR 1. That would produce some result. This result is called a parity bit, such that if we remove one of the elements, so in this case, this would be data that had gone missing in a data node, what we can do is we can XOR all the other data that hasn't been lost along with the parity bit. If we XOR those, we can retrieve the data that was lost. This is a more efficient way of replicating data, and that's why it's used over making more than one copy of the same data. This example here of the XOR is actually pretty inefficient when it comes to erasure coding, so the algorithms they use are quite different and a bit more advanced. Okay, so in previous videos we went over these portions of the ingestion process. In this video we're going over the storage portion. How do we make sure that only a single instance of an event or record ends up in storage when all of these systems here could fail in some way? For instance, let's say we have a message that the clickstream logs produce. This message is then vended to a broker. The broker acknowledges or acts the host that sent the clickstream log, and then maybe prepares to send another message. But what if the clickstream producer here sends a message to the broker, so now the broker does have that message, and right before it can send the acknowledgement to the producer that it did receive the message, the broker itself goes down, or the network connection is slightly unreliable. Well, in that case, the acknowledgement from the broker to the clickstream producer that the message was received never gets acknowledged by this producer. So what happens then? Well, the producer will try to retry that message and send it again to the broker. In this case, the broker would now have duplicate messages and would really have no way of knowing that it should disregard one of these messages. Eventually, the storage layer would receive both of the messages. In some cases, this can be a slight inconvenience, such as seeing in the storage layer that a particular user canceled when they were already canceled from a subscription. In other cases, it can be far more serious if we're dealing in transactions of purchases. So how can we solve this on this producer-broker relationship end? So there's something called Kafka transactions that we can use. It effectively assigns a transactional ID to each record that's being sent to a broker, and there's a particular process that's followed with all the transactional IDs that are received, such that we can guarantee that once a message is committed to a broker, that same message won't be committed again. Kafka transactions can be somewhat cumbersome to work with, so Kafka Streams API can simplify that. So now we can deduplicate this message because we used Kafka transactions. Let's go ahead and send our broker's message down to the consumer. The problem is the same exact acknowledgement problem can happen between the broker and the consumer. So in this case, if the message does get sent, and then meanwhile, while this is trying to acknowledge, the broker goes down or the connection becomes unreliable, the broker will attempt to resend the message. And now again, we end up with duplicate messages in our storage layer. There's a multitude of tools that we can use, but one of them is the Kafka connector sync. This connector connects the broker and the consumer together, and specifically they created an HDFS sync that allows us to achieve that exactly once delivery guarantee. If we use this HDFS sync provided by Kafka, then the message will be guaranteed to be only sent and delivered one time. So now we can be quite confident that our storage layer doesn't contain any duplicated messages. So now how are these messages actually stored in our storage layer, which is HDFS? Well, we're going to go over two of the most common formats. Avro is row-oriented. What that means is that if we had this table here, so we had name as our key, and the values associated with this key were a particular schema here of this header, so city, high score, and year. This is keeping track of some game. Avro would represent this per each row. So here we would actually have commas for every single item in the row, and then we would end the line here and begin the next line with the same exact format. This is good for queries which need all columns for a particular user. It's also good for heavy write loads. As well, Avro supports a lot of schema evolution. So if we have data coming in from our clickstream and all of a sudden we want to add another field, or take away field, or change the field's names, then Avro is a good way to support that use case. Parquet, on the other hand, is going to represent the same table that we had in a column-oriented way. So here, if we translate this to what we had before, each item, in terms of its column, will be represented and split apart by a comma, and then this indicates the end of that particular column. So here's the first column, second column, third column, fourth column. This is good for queries which only need some of the columns. It's good for heavy read loads. However, the schema evolution support is pretty limited. And again, since we're going through each of these columns, it's really good for sparse data in the sense that if the entire column has sparse data, then we can just skip ahead to the following column. As well, we can compress those column values that are similar. So if we had that column for cities, and a lot of the people were from the same cities, then we could compress that city column a lot more efficiently than if we stored it row-wise like an Avro. Let's go ahead and see a demo here using our clickstream that we built in previous videos to now store items in HDFS. In order to get the HDFS sync working, we need to configure it through Kafka. So here we will configure the HDFS sync, just called HDFS3 because 3 is the version that we're using. And here we're actually creating the configuration for the sync connector. Most of these don't mean much to us right now, and that's okay. The only thing that we should really know is that we'll be writing JSON to HDFS for now. This is just for readability, so you could put Parquet or Avro here, but for now we'll just use JSON. As well, we have to know the topic in which the sync connector should listen. So here we'll just mark our topic that we created earlier called ML-Expert. And finally, the sync has to have some sort of destination in which to write the clickstream records that it obtains by listening to the ML-Expert topic. So here, the destination is just the master node of our Hadoop cluster or HDFS cluster that we started. The port for it is 8020. So let's go ahead and start the connector up. How we start the connector is this command here. So all this is doing is running a shell script that is included with the basic installation of Kafka. We're providing the quick start HDFS properties that we already saw, in which we're specifying the topic to listen to and the destination to send these records to, our HDFS cluster in this instance. And as well, we're also providing it another properties file, which is just default. We haven't changed anything about it. So after running this command, we'll be able to go to our simple interface here that we've created with our Flask server. And last time, we just typed the word hello, and our simple consumer displayed our message hello on the console. This time, the consumer will be that HDFS connector sync, and that will route all of the records to HDFS. In order to make sure this works, we should be able to monitor what's inside our Hadoop distributed file system. And we'll just go over to our HDFS name node. So this HDFS name node will give us a bunch of information about our running Hadoop cluster. It'll tell us when we started it, what version we're on, things like that. As well, it'll tell us how much capacity is remaining in our nodes. What's more interesting to us right now is the ability to look at the file system itself. So if we go over here to Utilities, we can browse the file system. And in this case, if we go over to Topics, we'll be able to find our ML-Expert topic. This directory, which matches our topic name, was created by the HDFS sync. So if we click into this, we'll get a single partition. If you recall, in earlier videos, we talked about Kafka partitions. If we click into this partition, we'll see that there's no data in here yet. So we can make data appear here if we go back to our simple Flask server that we have. And in this case, we're going to search the same term as we did before, hello. And we'll still get our same result of no results yet. That's just because that's what we've hard-coded into the search results. However, if we go back to our Hadoop directory and we refresh it, we'll see that an item has appeared in the Hadoop file system. And if we download this file and take a look, it will look the exact same way that we saw when we had the simple consumer running in terms of Kafka. Some things to point out is that we can partition by other things, so if there's some content in here in the JSON such as the region or the date, we can also make sure that the HDFS sync connector, which is attached to Kafka, we can make sure that it writes to those partitions by whatever we decide to partition on. Just before we wrap up the demo, since we showed the name node, this interface is actually running on the name node itself, we can now look at the data nodes. So here we only have one data node. It looks like the last contact was fairly recent, and it shows us how much capacity we have remaining for that data node. So in this video, we went over HDFS, which is Hadoop Distributed File System, which allows us to store up to tens of petabytes of data across a cluster of machines. We went over exactly once delivery through our ingestion engine, such that the data storage layer would have exactly once delivery guarantees. Finally, we went over different ways that we could store our data in terms of their formats within HDFS. That wraps up the data storage video for the large-scale machine learning section of ML-Expert. Thanks for joining, and we'll see you next time.